So More Armony is the Vice Dean and Faculty of Research, the Harvey Gola Professor of Business and a Professor of Technology Operations and Statistics at NYU. And when she's not busy with all of so yeah, but you know, more lately she's been known for kind of, you know, very strong empirical and modeling optimization skills and operations research skills, solving a number of important problems in service and operations and healthcare systems. So Moore's here to give us a talk on queue configurations and customer ownership. Thank you very much.
Thank you, Neil, and thank you so much for the organizers for inviting me. I think this is a fantastic idea of sort of around the world conference where everybody can find the time slot that matches their own schedule. I just realized that on the East Coast of the US, this is lunchtime. On the West Coast, it might be early breakfast or late breakfast, and in Europe, it might be dinner time. So consider this your mealtime entertainment. What I want to talk to you about today is queue configurations and customer ownership. It's an analytical and experimental investigation. So I will discuss two separate but related projects that I joined with Guillaume Roels and Hummy Song. One of them was a modeling sort of theoretical study, and the other one, which is still ongoing, is an experimental study. Now, I think Hummy is here, and perhaps Guillaume too. I don't know if I can see them on the panel, but once they come. Anyway, feel free to ask questions as I go along, and I will do my best to answer them. And if Hummy and Guillaume are here, they can help out too. I'm starting with sort of a classical queuing question, which is the benefits of pooling. Pooling servers to serve, pooling dedicated servers to serve a single queue, and what are the benefits of this? And this slide is actually taken from my MBA class, where we talk about, you know, if you have 3 identical servers, is it better to have them be in a dedicated sort of configuration where each one of them has his or her own queue, or alternatively to combine them all and pool them into a single queue system. And the discussion is always fascinating to see what people think about the configurations. But the main message we always end up with is that pooling is a good thing, because it helps mitigate the variability of the individual systems. The servers can help each other out, and overall, you know, when we do any sort of calculations of either waiting time or time in the system, pooled queue outperforms the dedicated queues. So this is sort of the existing theory. I know that there have been a lot of papers on this particular question with other nuances, which I will get back to momentarily, but this is the main pooling principle. Now, more recently, some empirical projects have been published that actually question this common wisdom. One of them is this paper that looked at the telecom call center, in which they were experimenting with moving away from a pooling system, from a single queue, multiple servers, into team-based structure, where each team, smaller teams, had its own queue, and they were dedicated to particular customers. And the idea that there's a team link to customers, they felt could actually outweigh the economies of scale that come from pooling. Another paper that was co-authored by Hummy Song, which was sort of the direct motivation for our work, was work related to emergency departments. And in these in this emergency department, there was a natural experiment where they moved away for a period from a pooled system into a dedicated system. So imagine patients coming into the emergency department and wait in the waiting room. There's multiple doctors. The question is, do you assign the patients to doctors ahead of time, or do you just send them to the next available doctor? So they moved from the pool to the dedicated, and they found empirically that even though the theory predicted otherwise, the dedicated configuration actually resulted in a 17% decrease in the average length of stay and a 9% decrease in the average wait time. So we see another example in which in practice actually dedicated queues outperform the pooled queues. There were a lot of different explanations that were ruled out, but the main explanation that seemed to come up from conversations with the physicians is this one right here, is a quote from a physician saying that now with patient allocation system, with this new one, I am responsible for getting my patients from the waiting room into my beds. I do this by making sure the tasks are being done so that I can discharge my current patients. So this notion of when you switch from pooled to dedicated queues, potentially the servers become more invested in their customers. As soon as they're being assigned to them, they feel like a sense of ownership over these customers, and therefore they make sure they get in and out more quickly. So this was our starting point for this project. And the question is, how come or why might pooling not deliver its promises? The literature does have, we're not the first to be looking at these questions, and there's a fairly large number of papers that look at different factors. Some of the factors are customer driven. Some of them are server related factors. We also organize them by exogenous factors versus strategic behavior. And I'm listing a whole lot of papers here. I would just mention that one thing that was has been clearly shown is that when we have either asymmetric customer requests or asymmetric servers, it does sometimes make sense not only to decouple the servers or have dedicated queues, but sometimes in the slow server problem to even not use the slow server. So this is an extreme case of preferring dedicated. Our work right here relates to customer ownership, which is a server related driver. So we're thinking about not how customers might impact the performance, but servers. And we're looking at endogenous factors or strategic behavior. The overall research framework, which is something I kind of like to think about as a framework that's really useful for us as queuing theorists, and very much ties into the theme of this workshop, is we have theory that we've developed throughout the years, not just we, you know, a long lineage of researchers. And then we have empirical results coming up. Sometimes the empirical research is to test the theory. Sometimes it's to test new phenomena. And perhaps things that come up from the empirical research justify revising our theory or revising our assumption and come up with new theory based on these revised models, which is what we do in the first paper. Once there's a new theory, one can either go back to the field and look at empirical results or run experiments. So what I'm going to describe today is based on these two phases. I first will look at the analytical results, or the theory-based, and then I will talk about our ongoing experiment. I see some messages. Okay. Okay, so the questions are from previous one. All right, so I'm starting with the theory part, and I'll right at the outset state our contribution. So in the theory part, we develop a formal game theoretic model that compares the average work in progress. We're talking about either the number in system or the sojourn time of pooled versus dedicated queues. Customers are randomly assigned to queues with no joking or bulking. These were both shown to mitigate some of the benefits of pooling. Servers are symmetric, so again, benefits of pooling should exist. Customers are homogeneous, and servers are paid a fixed wage, so there is nothing about compensation that plays a role here. The twist for our model, as opposed to the traditional queues, is that servers are strategic, and they strategically choose their capacity to balance the cost of customer ownership and the cost of capacity. So the idea is that if the servers experience customer ownership, which is has been documented in the behavioral literature, we attach a cost associated with this customer ownership. We also assume that the server incurs capacity cost, and they're choosing their capacities based on those factors. So the research questions for this particular project are that we looked at are the benefits of pooling still significant when servers are strategic and exhibit customer ownership? So we've added these two components, and the question is how do the benefits of pooling stand with respect to this change in assumption? We're defining scope of customer ownership, and the question is which queue configuration, pooled versus dedicated, outperforms the other one in terms of WIP, and whether these effects vary depending on the level of discretion that servers have over their choice of capacity. So we can imagine some services that have very little discretion, where Neil, related to the question you asked Galit earlier, there's some scripted answers, so there's not a lot of discretion, versus knowledge-intensive services in which the expert server can really use a whole lot of discretion in terms of the amount of effort and time to spend with respect to the customer. So I'm going to present the model, and the paper that was published in OR has some theorems and results that I'm not going to repeat here, but what I want to focus on is what is the model and what are our conclusions from the study, so as to motivate the experimental study that we follow up with. So we have, we're looking at the simplest case where we have two symmetric servers. We're comparing two MM1 queues versus one MM2, so two dedicated versus one pooled. We have a Poisson arrival rate, 2 lambda. So if the two servers both have exponential times with rates vector mu1, mu2, and mu I is greater than lambda. In the system of the two dedicated, we have random routing. So we have independent arrivals to the two queues, both each with rate lambda. First come, first served within each queue. And the choice of capacity is static. So we're not looking at models in which server might dynamically adjust the service rate mu, but chooses mu once and for all. And we focus on symmetric equilibria. In terms of the capacity costs, we look at a cost that looks like this. So a constant C times mu, which is a service capacity over the base, some base service level, normalized to 1 in this example, to the power of K. So K, we can think about is the elasticity of this cost. And without going too much into the details, the important thing to note is that for a lower K, the server has more discretion over their service capacity. Looking at the extreme where K is large, the cost of capacity goes up very, very quickly. So there's less discretion. When K is small, the cost of capacity is moderate, so that there's more discretion in terms of its choice. So lower K goes with more discretion. The other part of the cost is the customer ownership. So the way we model customer ownership is we're thinking of a server that internalizes the holding cost of the customers. So we're thinking that the server attaches cost HS per customer per unit of time for the customer in service, and HQ for the customers that are waiting in the queue. So for example, in a dedicated system, if currently there is L customers in the system in one of the queues, the customer ownership cost would be HS plus HK times L minus 1 and 0 otherwise. In the pooled system, there is a little bit more freedom in terms of choosing how to allocate the costs, because there's a single queue, so it's not entirely clear what the customer ownership is with respect to the queue. But the way we think about it is we think, the queue is L minus 2, assuming L is greater than or equal to 2, and the cost is divided equally between the servers. There's some other alternatives that one may consider, but this is the simplest case. We are in the paper focusing on two extreme cases. One that we call SysCO, which are trucks that deliver food. No, but this is basically the case where HS is equal to HQ. So the servers ownership of the customers is the same for all of their customers, regardless of whether they're in service or waiting in the queue. The other extreme is SysCO, which we think about the service customer ownership, where the server really only focuses on the customer that is in service and doesn't really pay attention to the time the customers have spent in the queues. So in the paper, we have analytical results for these two extreme cases and an extensive numerical analysis for more general values of HQ and HS. So what is the game, and why do we even call it a game? So in fact, if we think about the dedicated capacity, it's not really a game. It's a regular optimization, single parameter optimization, where the server chooses mu ID for dedicated to minimize their cost, which is a sum of the capacity cost plus the customer ownership cost. So there's no interdependence between the servers, so it's not really a game. However, in the pooled system, we do need to think about a game, because if Neil and I are both the servers, the way I would choose my own capacity may be impacted by the capacity that Neil chooses. For example, if Neil works really, really hard, I could probably eat my lunch and take a break, right? So there's a notion of free riding. There's a notion of one can count on the other. So for these games / optimization problems, we show that an optimal solution here exists given these conditions on the parameters. No need to remember this, but we need the both customer ownership parameters to be large enough. Similarly, with the game in the pooled queue, again, we need some condition on HQ and HS. Okay. Why might an equilibrium not exist? You might think that it should always exist, but since part of our condition is that the system needs to be stable, we're optimizing over a non-compact set of parameters, so you might not have an optimal solution. Okay, so we have existence of equilibrium given some conditions. And now we want to look at the two systems, dedicated versus pooled. And how are we going to measure it? How are we going to display it? So we are looking at the two systems. On the top, I'm looking at the total number in system times 2, because there's 2 independent dedicated systems, at the value of capacity mu d, which is the optimal capacity that one would choose. In the denominator, I'm dividing this by the total WIP, the total number in system of the pooled system, given the vector mu1 and mu2. And since we focus on symmetric equilibria, this is a vector with both entities are the same. So let's think about where would we want this quantity to be. So for example, I'll show another example. If the system owner was able to force the servers to use the same capacity, let's say mu d, we know from theory, from the benefits of pooling, that pooling always outperforms the dedicated systems, and therefore this number is always going to be greater than 1. more customers in the dedicated system versus the pooled system. In fact, we can show that as the traffic intensity increases, this number gets farther and farther from 1. So the benefits of pooling are even more pronounced when the traffic intensity is high. This is what we're trying to investigate, but we're going to use this as a benchmark. Okay. So again, we have a number of theoretical results for the 2 extreme cases, but I want to show just some numerics so we can get the intuition. So the first slide that I'm showing for the results is SysCO. SysCO, to remind you, is when the customers in queue and the customers in the service are weighed the same in terms of customer ownership. I stay with lambda equals 1 and k changes for the 3 graphs. The orange line is the potential benefits of pooling if we were to fix the mu as mu d. So we can see it's always greater than 1. And when h, the customer ownership parameter, is small so that the servers can work with high traffic intensity, the benefits are the largest. Compared to that, the blue line, which is what actually happens if we look at the choice, the endogenous choice of capacity by the servers, we see first the first thing to notice is that the blue line is always much closer to the baseline of 1 and much lower than the potential. In some cases, the blue line actually falls under the 1 line. This is an area where dedicated queues actually outperform the pooling queues. And notice that this happens more for small k. This is again the case where customers have more discretion over their service rate. So what we observe is that most potential benefits from pooling seem to be lost, especially when the holding cost is low and the cost elasticity is small. Okay. So, but what we do note for this SysCO is that overall, none of these numbers is too far from 1. So one could even say that practically it probably doesn't matter whether you use pooled or dedicated in this case. In contrast, if we look at the ServCO, and the ServCO, to remind you, this is the case where the server only focuses on customer ownership with respect to the customer who's currently in service. Here we see that the benefits of dedicated versus pooling could actually be arbitrarily large, and especially true when h is small, that is when we work in high traffic intensity. So high traffic intensity, to remind you, is where the benefits of pooling usually are the highest. And in this case, when servers experience customer ownership and are strategic, that's when the worst performance of pooling comes up. So again, the benefits from pooling are negative when they are potentially the largest. So the summary of findings from this theoretical part is, I'm going back to my original question, are the benefits of pooling still significant? We see that they're basically essentially annihilated, and we don't even see much benefits for pooling. For given scope of customer ownership, the queue configuration is almost irrelevant unless the customer ownership is very low. And we are in the ServCO scenario where servers care much more about customers and service than in the queue. We also see that the more discretion the server that has, the more beneficial it is to use dedicated queues. This is at some point where we sort of was the main results for that paper, but notice that all the comparisons I've showed you so far assume that when we compare the dedicated system to the pooled system, the assumption was that the customer ownership remains the same. If we go back to the motivation and specifically to the ED study, part of what they conjectured that might be happening is that in switching from pooled to dedicated queues, the servers start to pay more attention to the customer because they know that they're their own customers. And therefore, potentially the level of customer ownership actually increases. So in a sense, what they observe empirically might be both a combination of, yes, dedicated configuration can outperform pooled, but even more so if the customer ownership part increases with a change of configuration. So that's what I want to focus on in the second part, where we conjecture that this might happen, and now we want to test it and see whether this is the case. So any questions so far on the theoretical part? Neil, your face represents everybody's faces. You can't see anybody else.
So far.
Okay, great, thank you. So I'm going to talk about the experiment, and as I said, this is still ongoing. We're still writing this, and to me, this is the first time I'm presenting that part. So let's see how it goes. So the research questions that we look at in the experimental part is, what is the impact of queue configuration on performance? So whether we use dedicated or pooled queue, does it affect processing time? Also, is there a difference in customer ownership based on the queue configuration? And finally, does customer ownership mediate the relationships between dedicated queue and processing time? So this is the first level question. The second question that we're looking at that is consistent with the empirical study of the EDs is, what happens when the configuration changes? So what if you start with pooled and then switch to dedicated versus vice versa? So is there an anchoring effect of being in one type of queue configuration first versus the other? So can we see an effect on the order in terms of customer ownership? And can we see the effect of the order in terms of processing time? So these are the main questions. And we designed a study, actually separated into 3 studies, all pre-registered. The studies are all designed to study the same question, but we use different populations and different settings. So just to get used to this notation, in study 1, we're looking at a patient-centered task, and our population that we that participated in the experiment are all fourth-year medical students. Closest as we can get to the people who we're talking about here, which are doctors. To study, to see if the results are robust with respect to the population, study 2 focused on the same task, but this time the participants were MTurk workers. Finally, for study 3, we remained with the MTurk workers, but we changed the kind of task, which is a much more routine sort of a research assistance task that we anticipate will have less of a customer ownership component to it. See this medical chart and the difference in colors. I would go one study at a time. So the general setup is that each participant did the experiment twice, once with pooled and once with dedicated, but the order was different depending on the participants. So we had 2 conditions. Some of the participants went through pooled, then dedicated, and the other ones went through dedicated, then pooled. They complete 2 experimental rounds. And in each round, we are measuring, processing time, waiting time, etc. But we also at the end have some survey questions that are designed to measure the customer ownership. And we divide the customer ownership conceptually into 2 types of customer ownership. One is emotional customer ownership, where EOQ and EOS, where we're thinking about how does the server feel about the customer, how much do they care about them? And the kind of questions we asked are designed to elicit that. Q for the customers in queue and S for the customers in service. And the other one is cognitive ownership of customers in queue that we measure in terms of how well does the server estimate the queue length. So this is less of sort of an emotional response, but something that they have to pay attention to and count. So E here for emotional, C here for cognitive, changing a little bit the notation, and O stands for ownership. What does the experiment look like? Let's first, and this is a physician scenario, let's focus first on what they see in their task. What is their task? So they basically see a number, a name of a patient and an age. And they see a list of 3 different vital signs. And for each of these vital signs, they need to write down the minimum, the maximum, and the latest. So the latest is at 10 p.m. So they basically have to go line by line here, find the minimum, the maximum, and the latest. While they're doing it, so it's a patient name, so it's kind of a medical a personal, it's supposed to emulate a personal experience, and vital signs, something that physicians definitely pay attention to. We measure processing time accuracy, so how well do they do? Waiting time, throughput time, and throughput rate. So we measure this for every session for every participant. So this is the physician scenario. The RA scenario, in contrast, instead of having a name, just has a case number. And instead of having actual names for vital signs, they're just called VAR1, VAR2, and VAR3. So they're more likely to treat it as just numbers. The task is still the same, min, max, and latest. So these are the two scenarios in terms of what their task is. Now, in terms of the queue display, they see it on the left side. So there are 4 doctors, and one of them is you. This is the person who's the participant. For each doctor, we have the name of the patient that they're seeing, Webster, Acosta, Dixon, and Lowry. And we have patients who are waiting. So this is the pooled configuration where the waiting patients are waiting in a separate line. In a dedicated queue, they're going to see the same waiting patients, but they've already been assigned to the doctors, either to other doctors or to the participant, him or herself. Similarly, for the RA scenario, the pooled versus the dedicated, the only difference is that now we have case numbers instead of names. Okay. With respect to presenting the results, I'm going to first focus on just the queue configuration itself and not the anchoring effect. So focusing only on the second session, it's either dedicated or pooled. And we have the three studies. Study 1 is the physician scenario with a medical student. Study 2 is a physician scenario with MTurks, and study 3 is the RA scenario with MTurks. And we're going to test these things. So I'm going to start with study 1, walk you through those results, and then focus on what's different or similar with the other studies. So study 1, again, the red is medical students in the physician scenario. So what do we see from this experiment is we see that comparing dedicated queue to the pooled queue, we indeed see a lower processing time a faster processing time. Yes, the shorter processing time, the servers work faster, sorry about that, in the dedicated queues, while not compromising on accuracy. So the servers work faster, but in terms of the accuracy of how, what is the quality of their work, there's no significant difference. We also see that the wait time and the throughput time measures are lower under the dedicated queues, but there's no difference in the throughput rate. So this is kind of the first order measure, is how fast the server works, and this is a consequence of these measures. So these are the results here. In terms of impact of queue on customer ownership, we see the following. So this is for the emotional ownership of the customer in queue. We do see that in the dedicated queue, the servers experience more ownership of the customer in queue. There's no significant difference in how what they experience towards the customer in service. And again, there is a significant difference in terms of their ability to estimate the queue. In both cases, they overestimate the queue length. Difference in, yes, they underestimate the queue length, but in the dedicated queue, they don't underestimate it as bad. So they're more accurate in the dedicated queues. The third part is the mediation effect. And here we didn't include in the model the emotional owner of customer in the service because that comparison was not significant. We see the following. We see that actually for the EOQ, the mediation effect is negative, meaning that the more emotional ownership of customer in queue actually makes the server work a little slower. even though in a dedicated queue, the server tends to work faster, the fact that they have more emotional ownership of the queue makes them work a little slower. And one potential explanation is that they care so much about the customers in the queue is that they forget to focus on the one that they're serving right now. We have a positive mediating effect for the cognitive ownership in this case. So this was study 1. Study 2 is very similar. The results are perhaps the level of significance is not as high, but very, very similar outcomes. So I'm not going to spend time talking about this. And finally, for study 3, we see that there are no significant difference in terms of processing times and in terms of the other measures of performance with dedicated queue versus pooled queue. This is, to remind you, is the case where we expect the level of customer ownership to be the lowest because these are case numbers rather than names. We see that indeed in this case, dedicated queue does not outperform the pooled queue. For the impact of customer ownership, the only difference between the other ones is that now the cognitive ownership of the queue is not significant, but the signs of the mediation and suppression effects are the same. So now we look at the second question, which looks at the change in queue configuration. And the question here is, again, whether the fact that a customer started with pooled queue and then switched to dedicated queues, or vice versa, whether there's any anchoring effect that is lingering because of how they started. And again, with the empirical motivation that we had, we thought the fact that they switched from pooled to dedicated, there was this extra boost for this customer ownership, because all of a sudden you realize, oh, before they were just like names on a dashboard, and now they're my customers. So how do we isolate in this effect? It's not trivial because we do see in all of our experiments a learning effect, where from session 1 to session 2, the participants improve. So how do we separate the learning effect from the actual effect that we're trying to measure? So we're looking at the independent variable Yij, and this is the model that we're looking at. We have all the combinations of first pooled, then dedicated, focusing on dedicated. This is focusing on the second one, or first dedicated, then pooled, then focusing on the second one, or first dedicated, then pooled, focusing on the first session. And we're missing one more, but in order to be able to estimate, we had to drop one of them. And there is a participant effect and a case effect. And so let's say we run this model, we run a regression, and we estimate the betas. How would we show or illustrate that there is an anchoring effect, or how would we test whether there is an anchoring effect? So here's how we're thinking about it. Consider two effects that exist. One is the dedicated versus queue versus pooled, and the other one is the learning effect. The learning effect is something we didn't have in the previous slides because we only focused on the second session. Assuming that these effects are independent and there is no anchoring effect, beta 1 should be a combination of the effects of dedicated plus the learning effect, because We are in the dedicated, sorry, and the dedicated is the second one. Beta 2 has the learning effect because we're in the second, but doesn't have the dedicated effect because we're looking at the pooled. And beta 3 doesn't have the learning effect, only has the dedicated effect. So if there was no anchoring effect, we would expect, because D plus L is equal to L minus D plus 2D, we would expect that beta 1 would be equal to beta 2 plus 2 beta 3. So our test in this case would be, once we estimate the betas, to see whether they are significantly different or not. The left-hand side and the right-hand side. So what we see here for study 1, let's just focus on the last line here, is that when we look at the customer ownership measurements, those are both significant, meaning that that these results show that in terms of customer ownership, that participants that switch from pooled to dedicated versus dedicated to pooled had more change in terms of their customer ownership. But there was no difference, no significant difference in terms of processing time. Study 2 shows similar results, except now the emotional customer ownership is not significantly different. And study 3, we go back to being consistent with study 1. So all in all, what are the key takeaways? So regardless of the scenario, we're looking at the 3 scenarios, we see that dedicated queues lead to a higher level of emotional customer ownership of the customer in queue. That the emotional ownership of queue partially suppresses performance when performance is measured in terms of processing time. But the cognitive ownership of customers in queue actually mediates the effect on the performance of the queue configuration and performance. We also see an anchoring effect for customer ownership measures, but not for performance. In the scenarios where customer ownership is expected to be more salient, that is in the physician scenarios, when we see a name of a customer, the dedicated queues outperform the pooled queues with respect to speed without sacrificing quality. And the dedicated queues also lead to a higher cognitive ownership of customers in the queue. In scenarios where customer ownership is less salient, there is no measurable difference in performance or cognitive ownership of customer in queue in the queue configuration. So that's it. I kind of told you hopefully a full story of, starting with theory, then empirical results, then our modeling paper, followed up by our current experiments. Happy to answer any questions you might have.